So the problem states a wet solid mixture, the amount has been given 30 kg per minute, of calcium carbonate powder and magnesium carbonate powder. So these two powders are mixed, okay, 40 weight% each, moist with 20 weight% of water. So in 30 kg per minute, you have 40% calcium carbonate, 40% magnesium carbonate, and rest 20% water. So here moisture is water. Has to be dried in a dryer. Input is at 90 degrees centigrade and 1 atmosphere. So the input condition has been given. Overall particle size distribution is of geometric mesh type 1 to 10 millimeter range. So the PSD, the particle size distribution, is given. There is no particle up to 6th interval. Particles in 7 to 10 intervals are 20%, 20%, 40%, and 20% respectively. So we shall understand it better when we actually feed in the data. First problem is simulate a dryer in shortcut calculation method with exit moisture content of 2%. So this is the feed condition, 20 weight% of water. And exit moisture content is 2 weight%. So we have to reduce it from 20 weight% to 2 weight%. Use 50 kilowatt heat duty and pressure remains unchanged. So we have to calculate accordingly. Okay. So this is the first problem. The second problem is repeat this problem using 200 kg per minute heated and moist air as heating medium at 200 degrees centigrade and 1 atmosphere with 99.98 weight% of air and 0.02 weight% of water. So here it is said that it is a shortcut calculation, but we are using some heating medium as well. Okay, in the first problem, we do not have any heating medium. In the second problem, we have a heating medium, that is air, moist air. The moisture content is very less, 0.02%, but some moisture is there. And its flow rate has been given, the temperature and pressure has been given. And here we have to assume 0.1 weight% entrainment. In the earlier problem, there was no entrainment, but this problem, as there is air in the system, so there will be some entrainment. And outlet temperature is 120 degrees centigrade. In the first problem, we use 50 kilowatt of heat duty. In the second problem, we do not specify heat duty, rather we specified 120 degrees centigrade temperature. Okay. Now there is some continuation of this problem. This is about the co-current convective dryer, and this is about continuous contact dryer. Okay, so we will read it later. Let us not confuse first. Let us begin with this setup. Now for that, let us go back to the Aspen window. Let us go to the component ID specification. So we will have calcium carbonate and then magnesium carbonate. Then we have water. What else? We have air. Okay. Out of which calcium carbonate and magnesium carbonate will be solid. So they will not take part in any phase equilibrium calculation. Okay. Now go to methods. Let us use ideal method. Run. Okay. Now go to the simulation window. So already we have this model over here. We have to just rename them. So this is the solid input and this is solid output. Okay, before that we have to set the stream, which is mix ClPsD. Okay, and then the solids, it is geometric, right? Let us refer once again. So overall particle size distribution is of geometric mesh type 1 to 10 millimeter range. So it is 1 to 10 millimeter range. So create PSD mesh. And then there is no particle up to 6th interval. So 1, 2, 3, 4, 5, 6, there is no particle up to this interval. So we don't bother about it. 7, 8, 9, 10, these intervals will have 20%, 20%, 40% and 20%. Okay, so that will cover 100% particle size distribution in the higher side. Okay, and you have to specify the moisture component. So water is the moisture component in this stream class that you have to set. So moisture has been set, and now go to the S in. Yes, now this Cl solid is open for you. Now the data has to be given 30 kg per minute, 90 degrees centigrade, 1 atmosphere. So it is 90 degrees centigrade, 1 atmosphere, and it is 30 kg per minute. And the mass fractions, it is 40, 40, 20. So it is 0.4, 0.4 and 0.2. And we have to place the particle size distribution. So there is no particles up to 6th interval. Particles in 7 to 10 intervals are 20, 20, 40, 20. So up to 6 there is only 0. No particle over there. And 7th is 20, 20, 40 and 20. So that is how the particles are distributed. So S in is defined. Now go to the block once again. Now open it. So this is continuous and shortcut. Okay. Pressure. Pressure is 1 atmosphere, right? So the pressure, it operates at, so pressure remains unchanged in this problem. So let us say 1 atmosphere. So pressure is 1 atmosphere and heat duty is 50 kilowatt. So heat duty is 50 kilowatt. And the exit moisture content is 2%. So exit moisture content is 0.02. Okay. And let us choose dry basis. So all the calculation will be done in dry basis. Now the system is ready to run. Let us run the system and check the stream results. Yes, so it is run. So just go to the result summary, streams. Yeah, you'll find two streams. One is input, one is output. Now, if you see, there is an increase of temperature from 90 degrees centigrade to 100.018 degrees centigrade because of the 50 kilowatt of heat duty that we have provided. So this temperature increase is the result of that. Now, if you go further down, your mass flow will be same, right? Both input and output. From this data, you will not be able to conclude anything. You have to check the mixed substream and Cl PSD substream separately. This is the mixed substream and this is the Cl PSD substream. Now let us go to the second problem. The second problem says repeat the problem using 200 kg per minute heated and moist air, and there instead of 50 kilowatt heat duty you have to use 120 degrees centigrade exit temperature, and you have to consider some entrainment also. So we have to feed in this information. For that, let us go back to the simulation. So here you have to add in another flow. So this is inlet gas and this is exhaust. You name it A in, that is air in, and you can name air out. And this air in and air out, air in you have to specify. Let us check the condition. 200 degrees centigrade, 1 atmosphere. (200 kg per minute). (99.98% air and 0.02% of water). So this is 0.0002 and this is 0.9998. That makes it total 1. And there is no solid portion over here. Don't bother about Cl solid. Now we have to change this model a bit. In this case, our temperature will be 120 degrees centigrade. And the entrainment in the Cl PSD it is how much? 0.1 weight percent. So 0.001. Okay, this is 0.1 weight percent. So this is the overall entrainment that we have. Okay, so again, it is ready to run. All other parameters we leave it same as the previous problem because it has been asked to repeat the problem, not change anything else. So run it. Yeah, so it has run very fast and results are available. let us go to the stream. As expected, two new stream has been added, A in and A out. And you can see the temperature has come to 120 degrees centigrade. So that is exactly what we were looking for. The outlet temperature to be 120 degrees centigrade. And it has come, both A out and S out, the outlet temperature, they are at 120 degrees centigrade. Pressure does not change, it is 1 atmosphere only. Now let us go to the mass flow. Now here you can find the entrainment. What is the entrainment? This one. This is the entrainment, because A out means air out, and air out is taking some solid along with it. And what is the amount of solid? For individually, calcium carbonate and magnesium carbonate, it is 0.72 out of 720, which is equal to 0.001. And that is the entrainment we have selected, right? And what about the other things? Like if you see the solid substream, the exit moisture content is still 0.02. We have not changed. So we have to check what is the result of that. So check it. So this is 28.7712 by this one, 719.28 multiplied by 2. This is equal to 0.02. You calculate, you will find that. Now we go to the next problem. It says, repeat the exercise with co-current convective dryer of length and residence time. The solid's residence time has been given. Equilibrium and critical moisture content dry basis, they are also given. And mass transfer coefficient has been given. The normalized drying curve data are also given. Okay, so instead of that shape factor F, which ran from 0 to 1, instead of that, they are giving the drying rate data. Okay, so solve this problem. It is of convective dryer. So for that, let us go back to our simulation window. So we change it to convective dryer, and it is in co-current. So choose co-current. The length and residence time are 6 meter 3 hour. So this is solid residence time and length. So length is 6 meter and residence time 3 hours. Okay. Go to the drying curve. Mass transfer and heat transfer data. It says mass transfer coefficient is 0.005 meter per second. So you can specify directly 0.0005. Okay. So it still shows some incomplete data input. Why? We don't know. Okay, so it considers indirect heating. So we don't consider indirect heating. So while we are discussing, we clicked it, so it was on. But for this problem, we do not need this information. Go to drying curve. Okay, so this information you have to provide. Equilibrium and critical solid moisture content are 0.5 and 1 respectively on dry basis. So it is 0.05 and 0.1 respectively. And normalized drying curve model data has been given. So 0, 0.1, 0.2, let us write is 0, 0.1, 0.2, 0.35, 0.65, 0.85, 1. 0.35, 0.65, 0.85, and 1. 0, 0.1, 0.5, 0.8. 0, 0.1, 0.5, 0.8, 0.9, 0.95, 1. 0.9, 0.95, and 1. So you might remember how that normalized drying curve function looked like. It was something like this. It was f is equal to 1 and this is f is equal to 0. So all of them started from 0 and ended at 1. Our data also follow one of those curves. Only thing is that we do not know what is the f value, and that is the reason we are using the data. Okay, so all the specifications have been given. Now it is ready to run. Okay, so we have run. Now let us see the summary. So these are the result summary. So here you can find that the water content in the dried solid is still 129.978 kg. So out of 360 kg, only this much has been removed. This is still left. Okay. So this drying operation through the convective dryer is not very effective. In the earlier case, shortcut method, we had given our required end product. But in this case, we are specifying the process, and process is calculating the end product. Now let us repeat this exercise with mass transfer coefficient of 0.005 and identify the significance. So in the current case, our mass transfer coefficient was 0.0005, but in the revised problem, they are asking us to use the mass transfer coefficient that is 0.005. So 10 times of increase in mass transfer coefficient is advised over here. And I hope that with increased mass transfer coefficient, our system will work better. Let us see how better the system works. So let us go to the mass transfer coefficient 0.005. Okay. So we reduce 1 0 less and let us run it. Okay. It ran very fast. Now compare the result. Earlier, it was 129.978, but this time it is 0.72. So directly it has come from 129 to 72 because we have increased the mass transfer coefficient. Okay. Now let us increase the mass transfer coefficient more and check how low it can go. So let us use mass transfer coefficient to be, say, 0.006. Okay, and run it. Let us see how much change we find. And we find still it is 72. As if there is no change. Okay, so what is the problem? Or is there anything we are missing out over here? No. Just check what it is? It is 72 by 720 plus 720. How much it is? This is 0.05. Isn't it? So what is this figure? Does it ring the bell? 0.05 is our equilibrium moisture content. So really we cannot go beyond equilibrium. So the system has come to equilibrium. You really cannot go beyond that. Okay, the system has come to equilibrium. So identify the significance. The significance is the equilibrium moisture content. And then next problem. Yeah, this problem says, repeat the problem using continuous contact dryer with 6 meter of length. An indirect heating of 200 kilowatt is provided. Heat transfer coefficient between gas and solid in this unit is 0.02 and gas solid heat transfer area is 1000 meters square. So let us solve this problem. So for that, you go to the dryer specification, you check contact dryer. It is having 6 meter of length, so it is the same as whatever we have chosen for the convective dryer. So 200 kilowatt indirect heating is provided. So here 200 kilowatt indirect heating, and specify the heat transfer coefficient between gas and solids, which is 0.02. 0.02 joules per second per meter square per Kelvin. So we have to use joules per second per meter square per Kelvin. It is 0.02, right? Yes. And the gas solid heat transfer area is 1000 meters square. So it is 1000 meters square. So we have everything specified. Run the process. And we go to the streams. So we have got up to 51.4896. Okay, so this is how you solve the problem. With this, we come to the end of this lecture. We will come back with another interesting lecture very soon. Thank you.